All right, we've looked at a number of situations where we were dealing with objects that had a constant acceleration, and we've come up with some general equations to describe the way things behave with a constant acceleration. So we're going to try to put all those together and see if we can figure anything else out. So we know for objects with constant acceleration, there's a few things we've observed. First off, from the inclined plane lab, so in the inclined plane lab, we had an object traveling at a constant acceleration, and we discovered it didn't matter which ramp you were on, so different ramps had different accelerations. Everyone wound up with the same relationships, and so it was generally true, as long as you have a constant acceleration, that the final velocity of an object with a constant acceleration is equal to the initial velocity of the object plus the acceleration times the time. And we also figured out that the displacement of the object would be equal to 1/2 the acceleration times the time squared plus the initial velocity times the time. And then we also, from looking at the area under a velocity time graph, we figured out that a trapezoid was the most general shape that would cover all of our situations with a constant acceleration. And we figured out from our velocity time graphs, from the area under a velocity time graph, we figured out the general relationship that the displacement should be equal to the initial velocity plus the final velocity divided by 2, where you can think of that as the average of the velocities, times the time. And if you look at these three relationships that we found, they actually only use, despite how many things are going on here, there's only 5 variables. The only 5 variables we ever see are initial velocity, final velocity, acceleration, time, and displacement. And not only do they all contain the same 5 variables, each of them contains a unique combination of 4 variables. So this top equation doesn't include displacement, this one, second one, doesn't include final velocity, and this one doesn't include acceleration. But they're all true for an object that is traveling with a constant acceleration. And so, like, for example, this one. If you had a situation where you didn't know the displacement of an object, but you wanted to find the final velocity and you knew initial velocity, acceleration, and time, obviously this would be a good equation. But you could also use it for a situation where you knew 3 of the other things in the equation and you were looking for one of these, but you didn't have the displacement and you didn't care about it. So if you knew the final velocity, you knew the initial velocity, you knew the acceleration, and you wanted to know how much time it was going to take, but you didn't know the displacement, this would be a great equation because you don't need the displacement to use the equation. Likewise, different problems are going to have different combinations of information that we have access to or that we're trying to find, and so we can pick the appropriate equation. And so it seems like, since there's 5 variables and we found 3 equations, each of which is missing 1 variable, there should be 2 other equations. And so we'd like to see if we can figure out what those last 2 equations are. So can we find a relationship that is independent of time? So all of these equations have time in them, which is great if you know the time or you're trying to find the time, but you could potentially run into a situation where you have the other 4 things. You know the initial velocity, you know the initial velocity, the final velocity, the acceleration. You want to know the displacement. You don't know the time, and you don't care about the time. And so we'd like to be able to come up with an equation that would let us just solve that directly. And so the way we're going to do that is by combining two of these equations via substitution. When we combine equations, we generally want to start with the simplest equations, the ones that are going to be the easiest to work with. And so that's probably going to be my first one and my last one. At this point, I know I have been really diligently writing the little arrows over each one of these. I expect some of you have abandoned doing that. And while I'm doing these derivations, I'm not going to bother writing the little vector signs over. We know they're supposed to be there. We know these are velocities. We know this is a displacement. When I get to like final versions of the equations, I'll put them back in. But when you're showing your work, it is okay to not constantly have to write this little arrow over it. So, my two simplest equations. Final velocity equals initial velocity plus acceleration times time. And displacement is equal to initial velocity plus final velocity over 2 times time. Okay, we would like to find a way to substitute these together to get rid of time. And so there's a number of mathematical approaches that you could use to do that. I would like you to try to do that. I would like you to pause the video and see if you can combine these together and get a single equation that has the four things other than time. So the only thing left is final velocity, initial velocity, acceleration, and displacement. Time is gone. So go ahead and pause the video. Try to do that. Unpause when you are ready to see the answer. Okay. I'm going to go through this. I'm going to do a way to find this. If you did a different thing that is mathematically equivalent, that is fine. My final form of the equation is going to be the cleanest and most useful version of it. And so if I wind up with something that is mathematically equivalent to yours, but yours isn't quite the same form, that's okay. But you're going to want to either manipulate your equation to match the form mine is in at the end, or if you want to just copy all of my work down, it's up to you. So one way to do this, if I want to get rid of time, is I can pick and solve one of my equations for time. And so I'll maybe take the top equation and solve that for time. And so if I rearrange this, I'm going to get final velocity minus initial velocity divided by acceleration is equal to time. And now I can take and I can plug that in for time here. And so we'll get displacement is equal to initial velocity plus final velocity over 2 times, instead of time, I'm going to use this thing, final velocity minus initial velocity over acceleration. And that equation is, I suppose, actually sufficient. It did what we wanted to. It's super ugly, though, and it's not going to be easy to work with. And so we're just going to clean it up a little bit. The first thing we're going to do, multiply everything together. And so I've got to FOIL this. So I've got to get all my terms combined. So I'm going to get displacement is equal to, let me maybe rewrite this as V naught plus V times V minus V naught over 2A. That might just be a little easier for some people to follow. So in the numerator, that's going to be V naught times V minus V naught squared plus V squared minus V naught over 2A. I'm going to take and multiply my 2A over here and also combine I have a V naught times V and I have a minus V times V naught. Those should cancel each other out. And so if we combine those, we get 2A times our displacement is equal to negative V naught squared plus V squared. And then the last thing I'm going to do is just rearrange this a little bit so that I don't have any minus signs. And so if I'm actually going to flip it around too. So v squared equal v squared minus v naught squared equals 2a delta x. And then if we bring this term over to the other side, we can get v squared equals v naught squared plus 2 times a times delta x. And so I'll put my vector signs back in here. What this equation is telling us is that the final velocity squared